Welcome, ladies and gentlemen, to the third presentation this morning, and a particularly interesting one for me, I think, this one, the citizen science, which we were having a chat earlier, and Gwyn and I, and we were just saying how technology has moved on and how accessible it's all become. So I'm very interested in this. Ladies and gentlemen, the citizen science and radio science. Gwyn.
Thank you very much. Well, good morning all, and it's my great pleasure and thanks to the RSGB for giving me the opportunity to speak to you today about ham radio science, citizen investigation, connecting communities. So take those two words away with you, connecting communities, and the communities being that of the professional ionospheric physicists, scientists interested in space weather, and us, the amateur radio community. And I'll explain along the way how any of you can become involved in these activities. So my background has got nothing whatsoever to do with radio science. I am a true citizen, a citizen science in this topic. My background was in oceanography, but I'm going to try and connect the two disciplines for you to show that my professional career, 40 years, was a mere apprenticeship to get me started in trying to investigate the ionosphere as a radio amateur and a citizen science. So up here on the top left, we have the aurora as seen from the International Space Station, which is orbiting the Earth within the ionosphere. 400 kilometers high is where it orbits within the ionosphere. And this optical image looking down sees the aurora, a wonderful image. On the top right-hand corner is another image from the International Space Station. You may recognize Spain on the top, North Africa on the bottom, and we're looking at the Strait of Gibraltar. And it's not an optical image, it is a synthetic aperture radar image, which for this talk has here entering the Mediterranean a group of waves. It's as if there was a pebble dropped in the middle of the Strait of Gibraltar and waves are radiating away. And that pebble was the tide coming in from the Atlantic over the sill in the Strait of Gibraltar and generating this packet of waves. They are gravity waves, as Jim said, but these are in the ocean. But my professional work involved using a sonar to look at where those waves originated. And they originated down there on the bottom right and on the interface between Atlantic water flowing in with the tide and Mediterranean water flowing out, and a sharp interface, as in sporadic E between them, and a wave-like nature on it. But look what a simple sine wave that is in the ocean. So my career was with simple sine waves generated in the ocean. But now let's move to the ionosphere on the bottom left. So what was the pebble here? The pebble here was a geomagnetic storm. Up in the Arctic, it generated a series of waves. Those oscillations there that you see in what I've labeled as one hop F2. So there's Doppler shift is on the left-hand axis. So on the y-axis, we have Doppler shift from -4 to +4 hertz of WWV 10 megahertz signal. And we can see the E region, not sporadic E region, as the nearly flat line, but F2 hop, 2 hop F2 kicks in towards the middle of that record with twice as much Doppler shift. And then the fuzzy, ghostly background is a mode 2 hop side scatter, which we'll come across later. So all of that information, all of those propagation modes are happening at the same time on this simple path of 10 megahertz. That's why it's difficult and challenging to really investigate the ionosphere. There are many things for us to learn. So we come in with HamSCI. So it's a collective. It's not a formal organization. There are no membership charges. There's no real oversight board, no formalities, entirely informal, that allows university researchers to collaborate with radio amateur community in true scientific investigations. In some of their grant proposals, amateur radio is there in the title. It's not an add-on, it's not an option, it's there in the title. It's the reason why they have been granted funding by the US National Science Foundation and NASA and others, involving several £100,000 for amateur radio related research. There is so much to learn that they are funded to do this work. It's to encourage new technologies, and I'll show some examples of those, and educational opportunities from students and citizens, as well as expanding our own knowledge as radio amateurs. So here's a dictionary definition of citizen science. It is scientific work, and it's done by ordinary people. We, radio amateurs, we are ordinary people as regards this, in these sorts of investigations. We do not have, some of you may well have, special qualifications. I certainly do not have special qualifications. But what I do have are transferable skills from my background in oceanography. I can look at data, I can visualize data, I can try and determine what am I seeing here. What looks like outliers? No, it's just that I don't understand yet why those measurements are telling us certain things. Now, NASA in particular is a terrific supporter of citizen science. There's over 30 projects, and HamSCI is one of them. Dr. Nathaniel Frizzell, who founded HamSCI, has, his most recent grant from NASA, there we are, $481,000. This is serious research funding going into amateur radio activity. So the citizen science focus for HamSCI, so recent projects have centred on the solar eclipses of 2023, an annular eclipse in October 2023, and a total eclipse over North America in April 2024. Those have been really serious efforts involving hundreds of scientists and radio amateurs. And really a continuing strand through HamSCI research is on travelling ionospheric disturbances, TIDs, which we'll come across. And the data for those come from PSK Reporter, WSPR, Reverse Beacon Network. So as radio amateurs, you would have been contributing to those research efforts without actually knowing it, merely making a WSPR or an FT8 or an FT4 contact. Your data will have been used by the research community. So what are some examples of amateurs and scientists working together? The field is broad. It's not just data analysis. There's building, from simple equipment, which I'll show on the next slide, through to coding, both Python coding, doing DSP, database, bringing the data together, data visualization of coding, operating. As I've mentioned, just by doing your own operating, doing your own thing, you'll be contributing to science. Or, as in that little photograph of three good friends of mine below, going portable during the October 2023 eclipse to the Nevada desert, and putting up a transmitter there right under the path of maximum obscuration. Or data analysis, which is mostly what I get involved in. So a wide range of activity. It's an inclusive community. It really is. So here's some examples of those four areas of activity. So building, and you've got to have acronyms if you're putting in successful proposals. So how about the Great Radio Amateur Propagation Experiment, the GRAPE? There you are, you're halfway to being funded already with that. And the engagement there was with technical staff at Case Western Reserve University in Cleveland, Ohio, and the Case Amateur Radio Club, W8EDU, and especially John Gibbons, N8OBJ, who came up with the very first version of the GRAPE receiver. And you will recognize the architecture of that very simple SDR with an IF of 1 kilohertz. And what's different about it, what makes it a scientific instrument, is the GPS disciplined oscillator, a phase-locked GPS disciplined oscillator that will give precise frequencies so that we can measure precise Doppler frequencies at 10 megahertz and so on and above. That's what makes it a scientific instrument. And the data reporting. So the Grape 1 is a build it yourself. Grape 2, given the success of Grape 1s, you know, you always want more bands. So Grape 2 did 3 bands, it moved to surface mount. So for most people, that's not really an option to build yourself from components. So it's pre-assembled, and the grant funding enabled 30 to be deployed to amateur radio volunteers for the April 2024 Eclipse. So here's another flavor of a contribution by a radio amateur to the HamSCI collective's objectives. So a very good friend of mine, Rob Robin at AI6VN, thought, well, let's use commercially available hardware, an SDR. And we already know that we use the GPS disciplined oscillator and the UK product from Leo Bodnar, a superb device. The RX888 Mark II SDR is a little bit of a niche product. It doesn't have an FPGA installed. That's an advantage in this case. All it does is it gives you 64.8 megasamples per second, so that's over 2 gigabits per second over the USB 3 link into a PC. So Rob thought, okay, well, this is a great SDR. How on earth do I handle 2 gigabits per second over USB 3? He knew the answer. He knew this amazing chap called Phil Kahn, KA9, and that's George smiling. There's some name, brand recognition for KA9Q, Phil Kahn, a true pioneer and innovator in DSP. So Phil has come up with what's called KA9Q radio, available on GitHub, and it's a general purpose open source software using fast convolution and IP multicast to digitally download, convert, demodulate, and distribute hundreds of simultaneous channels at baseband. So he takes in the 2 gigabits per second from the USB 3, and every 20 milliseconds he takes in new data into an FFT. The FFT is over the entirety up to 30 megahertz with 40 hertz bin size, and he's carefully chosen low prime factors to get the FFTs to really work well and efficiently. So it's as if, and I put as if in italics there because you don't actually see a waterfall of 30 megahertz with 40 hertz resolution, but that's what you've got internally. And then he generates a passband filter around your frequencies of interest, converts back to the time domain using an inverse FFT, and so you can have hundreds of WAV files in parallel at any frequency in that band that you desire. Okay, so we've moved the headache on now. How do we deal with hundreds of WAV files at a time? We come back to Rob, who had already developed a system, Whisper Daemon, for dealing with a few dozen WAV files at a time, in that Whisper Daemon takes in multiple WAV files for the Whisper channels up to 30 megahertz using the standard decoders in WSJTX, Whisper D and JT9, and sends that information to whispernet.org. Rob had then added the decoders out of WSJTX for FT4 and FT8 for all HF, MF, LF bands, and send those data results to PSK Reporter. And then he added on a capability with Franco K4VZ to look at the standard time station, the standard frequency stations, WWV, WWVH, and CHU. So from 2.5 megahertz, well, we'll forget 60 kilohertz down here, up to 25 megahertz. So all of those signals coming out of KA9Q radio in digital form are then sent on to the appropriate data networks by the Whisper Daemon software. So this was amateurs collectively doing this to support the science goals of HamSCI. But it's not just reception. What about modern methods in software-defined radios as transmitters? So here's an example by another HamSCI member, Paul Elliott, WB6CXC, with the Whisper Sonde. So the goal is to transmit stable and accurate multiband Whisper and FST4W modes, which is a beacon mode much like Whisper, and with a CWID, and to do this on up to 8 bands simultaneously. So simultaneous 1 watt outputs on up to 8 bands, up to 50 megahertz now, and to combine these as to depending on to which antennas and multiband antennas you might have available. And so you just need one GPSDO to keep this lot in check and one 12-volt power supply. Once you've set it up with a computer connected, just leave it. And so here's a multi-band transmitter, 1 watt, 8 bands every 2 minutes in these modes. Let's go on to coding for a moment. And this is the net database that you will not unlikely to have heard of unless you're already a HamSCI member. So it's where those great radio amateur propagation experiment, great receivers report their data. It's hosted at the University of Alabama. It was specified by radio amateurs, but built by professionals with grant funding. And the web page there, and there's the address in the title, gives you a map. They're virtually all in the US right now, where you can select on which location you want data for. You can go down into a searchable list of stations and what dates and frequencies they have, and then you click on that, and you can get a quick look plot as down here. And the quick look plot gives you the Doppler shift as a spectrogram, which is what we're seeing in color. So we're seeing Doppler values from -5 to +5 on the y-axis, and we're seeing 24 hours, it's always 24 hours, on the x-axis, and then the color indicates amplitude. So the signal has disappeared here. Just before the band closed, then there was a burst, a rise in the Doppler shift. And then we have a simple peak amplitude plot at the bottom. So this is like data exploration. You can go see, is there anything interesting happening that day or not? And then move on to the next station or the next day. That's all done in the database. And so what does the network of personal space weather stations, which is the name that they've given to this network, look like right now? Well, here's a snapshot from May this year with the tracks of the 2 eclipses. So the October 23 eclipse started in the North Pacific and then went over the western states and then ended over the Yucatan Peninsula around Mexico. And it crossed a great number of these stations, reporting stations, in the western United States, California, Utah, Nevada, and I'll show some of those data in a moment. And then the April eclipse, tracking over, starting off Mexico and ending over Newfoundland, was also very well covered by the networks of stations on the eastern side of North America. And again, I'll show some data. So, and in operating the 2023 and 24 eclipses, this inclusiveness, which is important for HamSCI. So not just formal members of HamSCI, but anybody could contribute. And using events that are quite familiar to the amateur radio community, QSO parties, encouraging activity during the eclipse, but also for each day either side, because you want to see the difference between a normal day and an eclipse day, and then a normal day. And the Gladstone, named after Phil Gladstone of PSK Reporter fame, the Signal Spotting Challenge, so for the WSPR and FST4W modes, to get information from them. And combined, for the October eclipse, over 750,000 data points from the amateur radio community provided to the professionals, and over 1.1 million for the April 2021 eclipse. So they have a tremendous amount of data because of the amateur radio community's involvement in these experiments. So what about some of the results that have come out of the HamSCI, the citizen science part? So this is an example by citizen scientists interested in medium wave propagation. So this is for the October eclipse of enhancement in signal level compared to a normal day. A normal day on, this is 1520 kilohertz, a broadcast station, so not an amateur transmitter, but received by an amateur. Broadcast station, 1520 kilohertz, and as the morning goes on, its amplitude decreases, and this is, of course, the familiar D region absorption at work. But on the eclipse day, you get the D region absorption kicking in, and then the eclipse, the obscuration starts, increases, reaches a maximum, and then falls off again. And so reduced absorption in the D layer leads to an increased signal level on this medium wave band. And Nick Hall-Patch and his colleagues have gathered this sort of information over many medium wave stations across the North America. So a particular interest of mine from analysis is to look at noise levels. How did they change? So we're looking again at D region absorption, but this time at 7 megahertz. And I'm calling it the noise anomaly on the left. That is the difference between 14th of October, the eclipse day, and the average for the same time of day for the previous 5 days at 2 stations, KFS and KPH, on the Northern California coast. And those are 2 old maritime radio stations. Our equivalent in the UK would have been Portishead, for instance, or Port Patrick Radio. But they are kept as working sites with their original wonderful antennas, and they are in low noise locations, and amateurs have SDRs embedded on those sites. It's a joy to work with that data. Hearing those is like going into the past as regards noise level. So what happens on eclipse day is that at both stations, the 2 colors of dots show the same pattern, a rise in the noise level. So as D region absorption has reduced, that means propagated noise coming in from outside, which we can't do anything about, has risen. So that's an interesting signal. So that means that if you're measuring signal to noise ratio, you've got to be careful because your noise is varying as well. If you should be interested in signal level, and so you've really got to measure your noise to make sure that your SNR, both variables changing, is not a good thing. You really need to understand and decouple noise from signal to noise ratio. And so when we do that on the right-hand plot, and now this example is on 80 meters in a path from Utah to Nevada, and the red dots are eclipse day, 14th of October, and you can see again that on 80 meters the signal level, and here we are talking about signal level, because we've taken the noise variation out, increases and then decreases again due to lower absorption on 80 meters. So these are observations you can make. Let's look at operating now with the grape receivers. So the grape receivers, we're going beyond looking at signal levels and noise levels, which is what we can do with WSPR and FST4W. Let's look in detail on the Doppler shift. So these spectrograms are images. So on the right-hand side, to remind you, we've got Doppler shift on the axis, -5 to +5 Hertz shift, around 0 line on the center, and we have 60 pixels, 1/60th of a Hertz resolution in the frequency domain. So this is like a high-resolution waterfall on its side, and with time of day there for 24 hours. And we can see that around dawn, there is positive Doppler shift. So what's happening there is that the path length is decreasing because the height of reflection of the signal is falling. So we can see that as a Doppler shift of the order up to 1 Hertz at 10 megahertz. But that's what happens at dawn. So during the eclipse, which is a dusk quickly followed by a dawn, we see the pattern there of a reducing, more negative going Doppler shift, and then followed by a positive going Doppler shift, and then returning to 0. So we can see a perturbation to the ionosphere, the height of reflection due to the eclipse. It's a nice controlled experiment. But let's go beyond quick look. I've seen that that data set is nice. It's clean. There's no interference on it. So there's the spectrogram, which I've blown up now. So -1.5 to +1.5 on the top in terms of Doppler. But that's still an image. That's still an image. How do I get digital values of Doppler shift? I've got 2 algorithms. That's really for another talk. But autocorrelation algorithm, which is dead simple to implement, is in black. But as you see, sometimes, like here, for instance, it gets some spots wrong. It gets wrong values of Doppler shift. Or a more complex FFT-based spectrum analysis coupled with a technique of continuous wavelet transforms to identify the exact position of the peak. I can interpolate between the 1/60th of a Hertz FFT bins, gives me the values in red as a digital value for the peak Doppler shift. Now, again, they say don't put equations on a presentation. They're there just for reference, and I wrote an article for Radcom, published in July of this year, on how to measure height of reflection from Doppler shift. I really want to concentrate on just the results on the right-hand graph for this talk. So the 2 algorithms are in magenta and green, and you can hardly say the difference between the 2 of them really until the very end here. And what have I got in blue and then into cyan is the cosine of the solar zenith angle. So that's the angle between the sun and directly overhead. So effectively, that's telling us time of day. Local midday is around here, and then the sun is starting to go down. And the blue function up here is the obscuration of the eclipse. So how much of the sun's area is covered by the moon. And you can see the maximum eclipse there. There's a 6-minute difference between the height of the ionosphere changing and the eclipse. That's all 6 minutes. I mean, I was absolutely delighted about this. It's a very simple cosine and then the obscuration. And yet that Doppler data that you saw from that so nicely matches that. Except look, the ionosphere reflection height seems to want to go up before it should. It's prejudging the arrival of the eclipse at the midpoint. Bosons. Well, it starts with a B, maybe. It starts with a B. The research community in just the last few years have been able to image a bow wave ahead of the eclipse. So the B, you were right with B. And so that there is a disturbance going on before the obscuration, the optical obscuration of the eclipse. There is a supersonic bow wave ahead of it. Is that what that is? Don't know yet. I mean, you know, you've always got to look for more data, collaborating evidence at other sites and other frequencies, but it would be really neat if that deviation was due to the recently discovered bow wave. You can operate using crowdsourced data. Here's an example of the eclipse for April 2024 across the Atlantic, where whisper transmitters from the UK received at North America their second hop over here, over Newfoundland, Labrador, and so on, was affected by the eclipse. And on 15 meters, which is this bottom heat map, so the color shows the number of spots received in these distance and time intervals, you can see that there's a big bite taken out of that. And that's because the second hop on these 15-meter paths from the UK to North America was cut off by the eclipse. The MUF dropped below 21 megahertz on these 5, 6, 7,000 kilometer paths. Now, the other focus for HamSCI has been large-scale and travelling ionospheric disturbances. The bottom example is from a professional radar at high frequency, and this is its beam here going up, and it's looking at effectively the skip zone. That's the distance at which propagation starts, the first hop starts. And that skip zone is modulated by these travelling ionospheric disturbances, and so the skip zone distance varies, and there with a period of about 2.5 hours. So Nathaniel and colleagues was able to synthesize the same sort and see the same sort of variation in the number and range of whisper transmissions received along a synthesized beam from all of those massive observations across North America. So he was able to match up amateur radio data with professional radar data, resulting in a well-received scientific paper. But you can move beyond that with the GRAPE receivers. So WWV, nicely placed in Colorado centrally, and here are just 4 receivers. They've got the yellow map pins, and the white map pins are the midpoints of those. And I was so intrigued on the 17th of May, looking at the quick lock plots, I saw wonderful waves. Now, from my second slide, you know, my professional interest in waves in the ocean, so here are waves in the ionosphere. Look, and those waves were received, you know, the midpoint up here between Washington State and WWV, and down here between WWV and down into Texas. Those waves were happening. They were traveling. That means that if you look at the correlation, how much in time do I have to slide the wave pattern from the northeast-west midpoint to the southwest midpoint until I get maximum correlation? I had to shift it 27 minutes. And on the orange pair, I had to shift it 35 minutes, and then I got maximum correlation. So that tells me the time it took for this wave packet to move that distance. So I can come up with a simple vector graph here, vector diagram, that shows that the wave was likely travelling at 909 meters per second along 154 degrees. And then you can back propagate that as to where it might have started if you know what your pebble was. And the pebble that caused the wave was this. This is the auroral electrojet index, and the geomagnetic storm, sudden onset, massive currents, millions of amps in the auroral electrojet cause heating, I squared R. If you've got 1,000,000 amps, I squared, you know, your R doesn't have to be very big, that's an awful lot of joules. The heating causes these waves to be generated, that's the initiation. And you back propagate and you end up with a region, likely source region, up there in the Arctic. So this is what amateur radio data can lead to, identifying large-scale internal waves. Now, HamSCI is very keen on promoting the next generation, in that communities that look to the future are effective communities and long-lasting communities. So at the annual HamSCI workshop, which I was privileged to be at March this year at Cleveland, Ohio, these were some of the young people, students, postdoctoral researchers and early career researchers that gave verbal presentations. Many more gave posters at their session. But these are amateur radio and radio-related titles from those young people, mostly with call signs, contributing to this effort. It's a joy to see. But it's not just in the United States. Professor Catherine Mitchell, M0IBG, Professor of Radio Science at the University of Bath, she convened a conference for HamSCI alongside this convention back in 2017. And more recently, 2 students, PhD students, doctoral students of hers at Bath, had amateur radio-related theses. So stress yet again, this, even at HF and VHF, it's not all known. It requires doctoral level research to which amateur radio can contribute, including our very own Chris Deacon. And I've been terribly grateful for professional guidance or guidance from the professionals on observations that I think I've made, but I'm not sure of. This is a supportive community. So I thought I'd seen something called the solar noise burst on 12 and 10 meters at some of these low noise sites in the US. This little bump here was an increase in noise level on different sites and on different bands. And I wondered if it was a solar noise burst. And the director of the Massachusetts Institute of Technology's Haystack Observatory, their equivalent of our Jodrell Bank, he bothered to read the post, to ask a distinguished colleague of his, Dr. Rogers, to see if data that he had from an observatory in Australia also saw a noise burst at that time. And indeed he did, and there's the graph, and it goes all the way from 40 megahertz down here, and this is 150 megahertz up at the top, or just off there. And so, you know, that collaborative information was wonderful. And HamSCI works to give us new tools. Ray tracing model, the PILAP model, HamSCI has made available via GitHub for us to do data analysis and propagation path analysis, and working on more comprehensive and physics-based models of the ionosphere. SAMI-3. SAMI is another model of the ionosphere, is what SAMI stands for, by Dr. Joe Huber, making this available to us as radio amateurs. HamSCI also influences the research agendas, especially in the USA. It sets challenges out for the next 10 years. So the HamSCI community wrote 2 papers to the US National Academy of Sciences Decadal Survey of Heliophysics. That's the equivalent of our Royal Society in the UK. So they wanted to know what are the research priorities, and in that radio amateurs made their contributions, and distilled it down into a scientific research paper published in Frontiers of Astronomy and Space Science, available to all to read that. So influencing the research agenda for the next decade. Getting involved is dead simple. Visit hamsci.org, click the blue button to join, and there are many, there's a central Google group, but then many specialized email lists, and on the HamSCI website there's a whole host of publications, or you can do it using Scholar and Google. HamSCI holds 3 Zoom calls every week. The one that I'm often on is Thursdays at 2000 UTC for the science questions and observations, and the other 2 technology and operations. So getting involved is easy. I'm not going to go through the acknowledgements. I just want to take you, I just want you to see the number of acknowledgements that are necessary for even this talk. There is such a wide diversity of people that have been involved, of grants from the Amateur Radio Digital Communications, ARDC, that supports this activity, as well as NASA and the US National Science Foundation. And the amateur radio community that's produced specific data for here, I acknowledge at the bottom there with grateful thanks. And I leave you with these links for further information. I've got a leaflet there with QR codes you can scan and a little fold-out booklet. Thank you.